Okay, so some more specifics on exactly how I'm trying to do this. I am currently in the process of trying to recycle or reuse this particular fan without this motor. I'm actually going to try to replace that really large multiple AC or multiple phase AC motor with a single phase DC drill battery, or DC drill motor rather. That seems really undersized, but let me just show you. This is a drill. Those are very similar to the thing in this. And I assure you, this is putting out quite a bit of air right now. So, and I'm not cranking this drill either, right? I'm just letting it do its thing at like maybe half or a third of its RPM, rated RPM. It is putting out a load of air though. That's what I could be doing. I'm not doing that though. So why is it that the little drill motor seems to perform comparatively to the really big motor? Well, that's because this fan also acts as what's called an airspeed governor, meaning that the faster you go, the harder air actually gets, the bigger problem air actually is. So this, like, let's say this thing outputs a certain amount of air. Let's say it's X, right? If I double the size and the power consumption of the motor, a lot of people might seem to intuit that would mean I would double the amount of air that the motor moves. That is not true. You will actually not double the amount of air it moves. You'll increase it by a little bit. And if you want to get more air to be moved, you have to increase the amount of power that the motor does by even more. So the larger amounts of air that you're trying to move, particularly if you're doing it with high velocity, you will consume ever increasingly more exponential amounts of power. It's called the law of powers or Pareto distribution, whatever you want to say. Middle squares law is another one. So these little guys here, they probably do not have nearly the performance of that. They probably have about 60% the performance, meaning that they can probably move about 60% the amount of air that the really big motor can. The kicker is that these guys consume like 20 watts. When this thing, I don't even want to think about it. It's probably around a kilowatt or 800 watts just for the motor. Little baby drill motors all the way, because I will take that large chunk of the air performance over the full thing all the time if it means that I get to if it means I get to sidestep the power consumption of that. So how efficient is this overall setup going to be? I do not know until I try it. That's why I'm trying it. I'm trying to build it first just to see. I will tell you that on the per watt cooling basis of how much you cool this area, the majority of what's being done, the majority of actual cooling is going to be coming strictly from ventilation. So if you can spend a watt taking hot air out, do that. Right? That's important. But if the outside air is actually too hot to be comfortable, then you do have to chill it. So when it gets to be 110 or 95 or whatever outside, ventilation isn't going to save you. It's just going to take really hot air and remove it with still too hot air. So you do need to have some kind of chilling chilling method. The way evaporative cooling fundamentally does that is we are putting the heat from outside, the outside air where it's like 100 and something, we're putting it into the water and evaporating the water into the air. That phase transformation represents an enormous amount of power. Now, it works wonderful for the little shed because the shed, as you see, catches rainwater. I do not have to pay a penny for any of this water. In fact, it in the summertime, when it rains a lot anyway, it catches rainwater a lot faster than I can use by putting it on my plants. And that's an application for rainwater. So each gallon of rainwater will represent for an area like this, probably 10 to 15 degrees of cooling for the entire volume of this area, maybe more. Forcing that phase change is what we're trying to accomplish here. And we're trying to accomplish that, obviously, with this few little watts input into the system. So I will have this fan, that fan, and a circulation pump. And I don't have to deal with freon. I don't have to deal with high voltages. I don't have to deal with anything that's going to kill me or hurt me or hurt plants or anything like that. It's like al natural. If you live in a place where it rains and you have a lot of water, you can use that water's evaporative properties to cool air or to cool yourself off quite a bit. So overall, this system will consume less than 100 watts comfortably. That fan up there consumes 2.5 amps, I know. Depends on what kind of pump I'm going to use, but I'm going to assume that the pump is going to consume about 20 watts. I'm on 12 volts, so 2.5 is about 30 watts. I have 30 watts invested in that particular fan up there. I have 30 watts in that. I will have another 20 watts, let's say, in the circulation pump. And then I will have, for these little motors, if I get them mounted properly, I will have probably another 20 or 25 watts, call it 30 watts. So I've got 30, 30, and 20. That is 80 watts, well below my 100 watt estimation that I just gave you. And I don't know how well it'll work. Here's how I suppose it can kind of get screwed up. It can get screwed up by not being airtight in here. So these doors right here, these doors just are not airtight by themselves. So if I have a nice ductwork here and an A-frame and stuff, that's fine and good. But if the draft pulls air through there instead of through my ductwork, or through these floors instead of my ductwork, then that chilling process is doing absolutely nothing. It's doing no good whatsoever. So that's a problem. It's an addressable problem, right? If I put weather stripping in here and if I seal up the rest of the place, that's not something that can't be relatively trivially overcome, but it is something that you have to deal with, which is kind of a pain in the butt. So yes, drafting, improper drafting. If you have a leaky place and you're pulling your draft, but it's not pulling air through your chiller system, that's going to be one way that you can lose a lot of performance really quickly, or to the point where it just doesn't seem like it's working at all, even though it would in theory. That's one way. Another thing that can screw you is if it's really humid outside. If you are at like close to max humidity or max humidity, you will not get any evaporation whatsoever outside. So you will not get any chilling or evaporative effect from outside when it's very humid. And that will really suck. So you won't get any AC when it's hot and humid, which it frequently is here. So you're going to suffer for those times. That's fine though. I don't actually live in the shed. I know it seems like I do, but I don't live in the shed, and that I can just avoid it for those days. Maximum humidity is fundamentally very unstable, by the way, so it can only ever last for small amounts of time. Well, not small amounts of time, but it takes ongoing processes that just are not very stable in order to max out humidity on Earth. Obviously, like humidity or the amount of water vapor you can keep dissolved in the air will drop tremendously with temperature. So this is why at night we get a lot of dew, because you are getting condensation of water vapor everywhere because the Earth has radiatively cooled, right? Like it's rotated away from the sun. It starts belching out all kinds of infrared radiation into outer space. Literally, this is the process by which it happens. And when it does that, the temperature drops, like the convective temperature or conductive temperature of the atmosphere drops, and water vapor precipitates right on out onto all your plants and stuff, and you get morning dew. So basically what I'm saying is, when it's very humid, wait for it to get cold a little bit. You'll get all the humidity on the ground, unless it happens to rain again. Just basically, so what, right? It gets humid sometimes, but around here, that's not a safe bet all the time. But come on, like I'm spending maybe 80 watts or 100 watts on getting the equivalent of a 2-ton AC system where they're cooling in the shop. I think that's cool. But for that reason, for the reason of not being able to control outside humidity or not be able to control performance due to outside humidity affecting it so much, for that reason, I wouldn't recommend such a setup for like an off-grid living situation, unless you're really tough and you are willing to put up with absolute misery if it rains a lot and it becomes very hot. So if you live in a place like Florida, this kind of setup would not be good for an off-grid living situation. It might coincidentally be good some of the time when it's not so humid. It might even work fairly well with like high but not maximum humidity. So it all depends. That's one benefit to it. Another interesting benefit about such a setup is that it's really flexible. Unlike with traditional AC, you don't have a lot of like narrow range dependencies. With traditional AC, this compressor has to be absolutely in sync with your ductwork. Everything has to be in proportion. Your ductwork has to be proportionate to the blower on your A-frame, has to be proportionate to how much condenser or how much freon you can collapse with your compressor, has to be proportionate to your everything. And if you get one of those things out of whack, you get like plugs of freon in your lines, you get bad things happening. This is a lot less demanding. It benefits from some passivity. So one of the bottlenecks of how much chilling you're going to be able to do is actually related to how much surface area you have on the outside coil. I'm putting water on the coil, and then I'm drawing air across that coil. So if the coil is enormous, then you are getting a lot of drop in temperature of the coil, and the coil is chilling the water that's being circulated within the coil, right? So if that's huge, you can get a lot of chilling effect off of that. Another interesting thing is that no matter how huge your exhaust fan is, if that was 10,000 CFM and it was basically like a freaking wind tunnel in here, you would still get a decent amount of cooling. Like this size system would be just fine. Like you don't cause any issues by doing that. It will effectively heat. What that will effectively do is heat the A-frame, which will heat the water, which will heat the coil, which will encourage more evaporation slightly, and so your system will actually work better depending on whatever your strongest element is. So instead of like, it's kind of like turning the whole principle on its head. And instead of the weakest link in the chain defining how strong the chain is, it's in this system, it's actually what's the strongest point of your system. If whatever's strongest kind of makes this system work as good as the strongest link in the chain, which is normally not the case. So that's an element of, I would say, good design, if I can say so myself, because like if you happen to have a really big exhaust fan, great, like your system will cool more or less bottlenecked by your exhaust fan. If you happen to have a ton of surface area out there on those coils, great. Then that will carry the efficacy of your system. If you happen to have one hammer knocking pump that just pumps and circulates water like extremely well, really quickly, then that will aid as well. Not so much, but that will be a strong point in your system. So it's not as bottlenecky and hard to engineer as traditional phase change, Freon stuff. Earth friendly, low voltage, low wattage, pretty flexible. Not too reliable, but to be fair, your actual house's AC is actually not. It is reliable but its efficacy is very dependent on humidity as well. These suckers actually happen to work better when it's very humid outside. So when it's humid outside in an actual AC system, the freon inside the condenser coil will collapse a lot more efficiently, and that will help your AC system work better. You'll notice that your AC system works fantastically well when it's raining outside, right? so that's a thing about them. Those don't actually work too well when it is bone dry outside. Your fan has to circulate a lot of air, and if it's really hot and really dry, those will not do so well. That's why out in like Arizona and New Mexico, you see a lot of popularity of swamp coolers, where people just simply have a membrane where they trickle some water across and pull a draw fan into their house, and they don't mind the increase of humidity, because that tiny increase of humidity from zero means nothing. In fact, it helps people not dry out and feel uncomfortable. So over there, a lot of people don't even use the same AC design that we're familiar with here. And they don't use it for very good reasons, because, again, they have no humidity to assist those systems in their efficacy. So they just straight up use swamp coolers. The fact that my system literally will not do any chilling whatsoever if you're at max humidity, that's not atypical for AC systems in general. Environmental effects or environmental conditions do affect any heat pumping system. If you're trying to move heat from one spot to another, from one section of the atmosphere to another section of the atmosphere, atmospheric conditions will affect the ability or methods by which you're trying to pump that heat. I think I have a valid design. I have a fair bit of tinkering and engineering to do, and I will let you guys know how it works out here at the friggin' backyard of infinite screwing around with things. so yeah, interesting. All right.